In this lesson, we will build one precise local picture. We begin with the definition of the partial derivative. Assume that the x partial derivative is positive, and then carefully separate a positive h from a negative h. Every sign will have a meaning. Let z equal f of x comma y, and focus on the point p0 with coordinates x0, y0. The function value there is f of x0, y0. Think of that value as the central height from which we compare nearby heights. For the x partial derivative, y is frozen at y0. We are not roaming freely on the surface, we move only horizontally in the x direction, so every nearby point considered here has the same second coordinate, y0. Now write the definition. The x partial derivative at x0, y0 is the limit, as h tends to 0, of f at x0 plus h, y0 minus f at x0, y0, all divided by h. The numerator is the change in height, h is the change in x. Assume this partial derivative exists and equals a positive number L. We are not merely saying that one quotient is positive, we are saying that the limit of the quotients is the positive number L. Because the limit is positive, all sufficiently small non-zero h give the positive difference quotient. This is the bridge from the positive derivative to the inequalities we want. The phrase sufficiently small is essential. Here is the rigorous reason. Choose epsilon equal to L over 2. When h is close enough to 0, the quotient differs from L by less than L over 2. Therefore the quotient is greater than L minus L over 2, which is L over 2, and this is positive. First take h positive, then x0 plus h lies to the right of x0 on the horizontal line, y equals y0. We now write the sign of every part of the quotient. The denominator is h, and in this case h is positive. We already know that the complete difference quotient is positive, therefore we are dividing the numerator by a positive number and obtaining a positive result. Multiply the positive quotient by the positive denominator h. The numerator must be positive. This is ordinary sign arithmetic, but it is the key logical step. Positive multiplied by positive remains positive. So f of x0 plus h, y0 minus f of x0, y0 is greater than 0. The new right-hand height minus the central height is positive. Add the central value to both sides. We conclude that f at x0 plus h, y0 is greater than f at x0, y0. Intuitively, a sufficiently small move to the right gives a higher value. Now take h negative, then x0 plus h is less than x0, so the new point lies to the left. The quotient is still positive because h is still sufficiently close to 0, but the denominator has changed sign. This time the denominator h is negative. Ask a simple sign question. What sign must the numerator have so that numerator divided by a negative denominator is positive? Multiply the positive quotient by the negative number h. A positive number times a negative number is negative, therefore the numerator must be negative. This is the point at which sign mistakes commonly happen. Thus f of x0 plus h, y0 minus f of x0, y0 is less than 0. The left-hand height minus the central height is negative. Add the central value to both sides. We obtain f at x0 plus h, y0 less than f at x0, y0. Intuitively, a sufficiently small move to the left gives a lower value. If negative h feels confusing, write h equal to minus r, where r is positive, then x0 plus h becomes x0 minus r. The statement is now visually clear. The point a positive distance r to the left has a smaller function value. Combine the two cases. Near the central point, values immediately to the left are lower than the central value, while values immediately to the right are higher. Remember that every point in this comparison has y fixed at y0. On the x-line, x0 minus r lies to the left, x0 is the center, and x0 plus h with positive h lies to the right. The corresponding heights go from lower, through the central height, to higher. So the correct intuitive sentence is this: along the horizontal slice y equals y0, the graph rises as it passes through x0 from left to right. This is the local x direction meaning of the positive partial derivative. This does not prove a local minimum. A local minimum would require all nearby values to be at least the central value, but we have just found sufficiently close left side values that are lower than the central value. It also does not prove a local maximum. A local maximum would require all nearby values to be at most the central value, yet sufficiently close right side values are higher. The point behaves like a rising point along this slice. Most importantly, this argument is only along the x direction. We kept y equal to y0 throughout. From fx being positive alone, we cannot conclude what happens if y changes, or if we move diagonally, or along another curved path. Let us test the picture with a simple example. Take f of x, y equal to x plus 3y, and use the point 1, 2. Fix y at 2 and move only in the x direction. The x partial derivative is 1, which is positive. The central function value is f of 1, 2, equal to 1 plus 6, or 7. Now compare nearby values directly. When h is positive, f of 1 plus h, 2 equals 1 plus h plus 6, which is 7 plus h. Since h is positive, 7 plus h is greater than 7. The right side is higher. When h is negative, the same expression is 7 plus h, but now adding h lowers the value. Therefore 7 plus h is less than 7. The left side is lower, exactly as the sign argument predicted. One final precision: positivity of the derivative at this single point compares nearby values with the central value for sufficiently small increments. By itself, it does not say that the function is increasing between every pair of points in an entire interval. That stronger claim needs more information nearby. Use this quick sign check whenever the negative case feels difficult. If h is negative and the quotient is positive, the numerator must be negative. Therefore, the new left value is smaller than the old central value. Here is the complete memory line. Keep y fixed. A positive x partial derivative makes sufficiently close left values lower and right values higher relative to the central point. It describes a local rise along x only. It does not prove a minimum, and it makes no claim about other directions.